Okay. So last time we started studying the semi-continuity of cohomology in flat families. Namely, I formulated some technical, very important theorem by Grothendieck. So let me repeat this formulation. So we have a flat projective morphism. Well, maybe, sorry, maybe I shouldn't say this, just projective morphism. And F a flat coherent sheaf on X. I mean flat over Y. Okay, and now we're going to compute its higher direct images, but not only its own higher direct images, but twisted by all the pullbacks from Y. So the claim is that there is a complex K of locally free sheaves on the base Y, such that for any quasi-coherent sheaf on Y, there are natural isomorphisms from the higher direct images of F tensor with pullback of M, and the cohomology, but local cohomology, just cohomology of complex of sheaves of K tensor M, okay, over OY. Okay, and we started the proof last Thursday. So first of all, this is a local claim. So over Y, and may assume we may assume that Y is affine, and we may further shrink Y as needed. Okay. Oops, sorry. Okay. So then we started with taking the Czech complex. So we chose an affine covering X is U naught and so on, U capital N. Okay, and considered the corresponding Czech complex.
Извините, можно спросить?
Yes.
А если бы гомологии были не подчеркнуты, то что имелось в виду под этими гомологиями?
Hell knows. Well, for example, there is notion of hypercohomology of a complex or whatever. But here I just mean cohomology sheaves. I mean, it's a complex of sheaves, so you can take the kernel of some morphism or the image of some previous differential and take the quotient, and this will be a sheaf. Okay, that's what I mean here.
Да, а если бы не было бы, как еще можно воспринимать это?
Well, there is also, as I said, there is a notion of hypercohomology. You can take cohomology with coefficients not just one sheaf, but with coefficients in a complex of sheaves. Okay, there is such a notion, or some other notions, but that's not what we are after here. So we can consider this Czech complex with coefficients in F, and this complex of A modules, and they are flat. I should say flat A modules, computing the desired cohomology. Yeah, but by the way, when I formulated Grothendieck theorem, I didn't say that this complex K was formed by locally free sheaves of finite rank. That's what very important, and that's what we'll struggle for. Let me add it here, of finite rank. Because eventually we're going to consider the Euler characteristic, and it wouldn't make any sense if we have infinite rank locally free sheaves. Okay, so as a first approximation, we take this Czech complex, and it works. The only problem is that those modules are not necessarily free, and they're of infinite rank. Okay, so now we need to produce some more economical substitution of this. So the desired okay, well, is the localization of a complex. Okay, straight like this of again of free A modules of finite rank, but well, we had it locally free, and now I impose free condition, so I allow to shrink my y.
А зачем локализацию берем? Чтобы пучок получить?
Yes. Okay. Okay. So now this complex K is, so to say, an economical or maybe economic version of this Czech complex. So the Czech complex is very big. Well, it's not locally free, but it's quasi-coherent. So it's not finally generated. But we're going to replace it by some more economical version. Maybe I should say economical. Okay. So let's go to the next page. And we'll prove some technical lemma. So I say that there is a complex like this. Well, I don't know. Maybe let me call it by some. Let me call it not K but L in order to distinguish, because because you'll see. I will demand something different from this complex, so it goes to some place Ln and then to 0. So it's a bounded complex. Of A modules and a morphism psi from this complex to the Czech complex. That is a quasi-isomorphism. That is induces an isomorphism on cohomology.
Извини, можно спросить?
Yes.
Чего мы добились на предыдущей странице?
I will answer in a moment, but just let me finish with this formulation. So there is a complex with a quasi-isomorphism such that L1 and so on, Ln are free, and all the terms Li are finally generated. Okay, so we wanted to construct this complex K of free modules. Yeah. And we succeeded. We almost succeeded. Well, if we prove lemma, we almost succeed. We construct a complex that of finally generated modules, and almost all of them are free. Just the very first one is not necessarily free. But then eventually we'll prove that even the very first one is free as well. Okay. Now back to Daniel's question. What did we do at the first page? Well, we constructed a zeroth approximation to the desired complex. Namely, it was the Czech complex. Okay, and it has this property in the Grothendieck theorem, but it doesn't have the finiteness property. So it does compute the desired cohomology, but it consists of infinitely generated modules. Okay, does that answer your question, Daniel? Okay.
Thanks.
Come.
Бесконечного ранга получается.
Well, Czech complex, like imagine that y is a point and x is the projective line for example, yeah, and then you have the standard covering of projective line by two affine lines. Yeah, you dispose of point 0 or dispose of point infinity, and let's say your sheaf f is just the structure sheaf. Then the sections will be polynomials in coordinate t or t inverse, right? And they're infinite dimensional. But what we want to have in this case is complex of finite dimensional modules.
Спасибо.
So that's what we struggle for. The proof is somewhat, well, it's straightforward, but technical, so to say. So we construct Li again by descending induction. So we put Li is just 0 for I big. In fact, I must be oh, so sorry, it's capital N. Sorry, capital N is the number of opens in the covering. So we actually need I bigger than capital N. So I have this Czech covering here, yeah, in the middle of the page, and I don't. Yeah, you can see it here. So capital N is number of capital N plus 1 is number of open sets in this covering. Okay, so we started just by taking trivial modules, and now suppose we already constructed Li plus 1 goes to Li plus 2 goes to so on. This is constructed along with psi. Here we have Czech complex, I plus 1. There is its own differential, plus 2, and so on. Is constructed. And now we want to construct Li. So how do we do this? First, we choose some generators of the ith cohomology of this Czech complex. So it's you know that this cohomology of Czech complex computes the higher direct image of our sheaf F, and we know that the higher direct images of the sheaf F are all coherent, so they are finitely generated, and that's why we can find finitely many generators. Okay, and now we lift them.
Извините, а почему найдется такое I, что Li будет равно нулю?
Because our Czech complex is bounded. It is bounded by this capital N. Yeah, in degrees higher than capital N, Czech complex vanishes, and we may take Li also 0 in this range. Yeah, it's
Li plus 1 и Li plus 2 равны нулю.
Yeah. If I is bigger than N, than capital N, then Li vanishes. But then at the place number capital N, something interesting starts happening. So we leave them to actual cocycles. And these cocycles will be called x1 and so on, xr. Okay, and also choose generators y r plus 1 and so on y sub s of the preimage under psi of the coboundaries. Okay, so we take the coboundaries in this well, in the next. Okay, so this D goes from the ith Czech complex to I plus 1, right? So we take those, and then we lift them to L, I plus 1, and then we set Y bar T is the psi image of those guys, and lift those to some elements x r plus 1 and so on x s in the ith Czech complex. Okay. Now finally we set Li. That, well, that's what we wanted to construct. Is a free A module with basis E1 and so on ES. And now we have to define the map psi. Yeah, so we have here this Li. It goes here, and to the I. This is psi. So we construct Li and want to define the differential D and the map psi. So we say that D et is yt for big T, and it is 0 for small t. Okay, and finally psi of et is just xt. Okay, and then you just immediately, straightforwardly check that it works. I mean that it is a quasi-isomorphism. First of all, that d squared is 0, and then psi induces a quasi-isomorphism. Okay, and in fact, psi induces an isomorphism in the I plus first cohomology, right? Because now we define the differential from Li into Li plus 1. And now it makes sense to check that psi induces the isomorphism in I plus first cohomology. And that is immediate from the construction. Okay, so this way we go on and on. But the only unpleasant thing I have to admit is that we never stop. Yeah, so our complex, our Czech complex, certainly started from C0. It lived in the non-negative degrees. It was bounded both from below and from above. And this complex L is constructed by descending induction. We started from capital N, and then we go down, 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 but we never stop. And that's bad. We wanted to stop at the 0th place, at the 0th degree, and that's why we don't have control over L0, because we have to truncate. So let's go to the next page. This way we construct an unbounded from below complex. So it's, once again, it's all good. It is free, finite generated, only it's not bound. And we define maybe I don't know. I have to introduce some other notation. Well, maybe L nu. So it's the truncation of this. That is, we said that L nu, say I, is 0 for I strictly negative, and L nu in degree 0 is the co-kernel of d negative 1. Okay? So then it's clearly finitely generated, but not necessarily free. Nu in degree 0 is not immediately clear to be free. So eventually we'll prove it in 10 minutes or in 5 minutes. We'll prove that it's free. But at this point, it's not clear at all, at least to me. Okay, so at least the lemma is proved. Yeah, well, let's recall what we wanted to construct. We want to construct some economical replacement of Čech complex consisting of finitely generated modules, such that almost all of them are free, all except the zeroth term. And that's what we did. Okay, so it remains to prove. That this L0 nu actually is free.
Можно спросить?
Yes.
Я упустил момент, где вот ключевой момент, где получается конечность вот этого построенного цикла?
Well, we just started this way. Say how did we start? We took generators of the ith cohomology, and then I claim that there are finitely many generators. But we know that our morphism is projective, so the higher direct images of coherent sheaves are also coherent, that is finitely generated, and also those higher direct images are computed via Čech complex. So the cohomology of Čech complex, each particular cohomology is finitely generated. Okay, and then we also wanted some other generators that are also finite for the similar reasons. Okay, so we've already used this finiteness theorem proved before last time or a week ago. Okay.
Извините, а вот этот dci, вот в этом месте он же образ d на чеховской итой группе, он же равен нулю, если i равно n.
You mean in the top place, or what do you mean?
Вот ближе к низу страницы вот.
Yeah. But
вот это не нулевой образ. Почему он не нулевой?
The differential or what?
Да, образ дифференциала вот этого.
The differential is not necessarily zero. Why? You have this Čech complex, and differential is not zero.
Но мы выбрали и здесь равно чему?
Well, we assume that we already know everything for I plus 1 and higher, and then we want to construct our complex L one step lower. So we know it for I plus 1, I plus 2, and so on. We want to construct it for I. Yeah. So, for example, yeah, for one thing, the Čech complex is infinitely generated. So when you take differential of Ci, it is infinitely generated, right? But it lives in degree I plus 1. This differential lives in degree I plus 1. And then you take its pre-image in Li plus 1. But Li plus 1, by construction, was finitely generated. So we take a certain submodule of this finitely generated I plus 1. But due to Noetherian property, any submodule of Li plus 1 is necessarily finitely generated. And that's what I use here. I use finitely many generators, y r plus 1 and so on, ys. Okay? So on the one hand, I used that the cohomology of Čech complex is finitely generated. On the other hand, I used that we already cover this, well, so to say, we cover this Čech complex by finitely generated complex L in higher degrees. Okay?
Почему L комплекс нетривиальный? Вот L-и-то, если I больше N, нулевое. А почему, если I меньше N, там будет получаться...
How does something appear? Well, you see that you at ith place you use the cohomology at this degree, and then choose the generators for Li from those cohomology, right?
Все, понял, спасибо.
Okay. So back to our business. We're almost done, but two essential things still have to be checked. First, that this complex we constructed, well, not the complex, but its zeroth term is free. For higher terms, we already know, and also that it works universally. Maybe let's call this A, and also there's property of universality, namely that for any A module M, if we tensor by M, then it is still a quasi-isomorphism. Okay, and then we're done. So that's what remains to be done. Okay, so let's do this. And to prove this, we'll use the standard construction of the cone. Cone of psi. So this cone of psi is another complex, and hopefully everybody knows this from, say, topology, I don't know, or basic homological algebra, but let me just recall how it works. There's a complex of A modules with an exact sequence. So we have this Čech complex, but somewhat shifted to this mapping cone. And to our complex L. Well, if you want L mu. So it's an exact sequence of complexes, short exact sequence of complexes. So I mean, it, so to say, commutes with differentials, and at each particular degree forms a short exact sequence of the terms of these complexes. So from this, we obtain the long exact sequence of cohomology. Cohomology of the Čech complex, and goes to ith cohomology of this cone, then goes to ith cohomology of LU, and so on. Well, it is defined just very stupidly as a direct sum. So this cone is the direct sum of Czech complex plus this new complex, and the differential is di of alpha beta is d I'm sorry d sorry di minus 1 alpha plus minus 1 to the power I psi of beta.
Дифференциал откуда куда действует?
Well, it's a complex, so it just raises degree by 1. Well, it's differential.
Это предпоследняя стрелка.
А?
Это какая стрелка вот в этой точной последовательности?
Well, it's from cone I to cone I plus 1. No. The exact sequence is for cohomology, but now I just defined this cone complex. You see?
Да, понял.
But just by definition, and then with this definition, clearly we have this exact sequence of complexes and exact sequence of cohomology, and in particular, we know that psi is an isomorphism, and hence the boundary map here, well, this boundary map, so to say, delta, and it's essentially psi, well, maybe plus minus psi. Okay,
А D0 чему равно?
Well, d negative 1 is 0, if that's what you ask. Okay, so this boundary map in this complex is 0, and hence, sorry, it's not 0. It's an isomorphism, because by construction the complex L was quasi-isomorphic to Czech complex, so the boundary map is 0, and the cone is acyclic. So in this particular case situation, psi is a quasi-isomorphism, and hence this cone psi is absolutely acyclic. Okay, and since it is acyclic, let us write down how it starts. It starts from the cone 0, then it goes to cone 1, then it goes so on. And what are those? Those are just L0 U goes to the 0th part of Czech complex plus L1, well, nu if you wish, and so on. Okay, and this is acyclic. In particular, L not nu is embedded into the next term. Okay, so this is an embedding, and we know, we also know that all the terms well, say cone bigger than 0 are flat, right? Because we proved this flatness for Czech complex already last Thursday, and this L nu is free at all. Okay, so everything is flat. Okay, but then it implies that L0 nu must be flat as well. Namely, flat means that say the first Tor of L0 nu with arbitrary a module M is identically 0. Okay, so the tensor product with L nu is exact. Okay, that's just definition. But if you compute this Tor via this resolution, you get 0. Yeah, and somehow it should not be confused with the opposite order, so to say, because every module has a left, say, free resolution, but free is flat. So every module has a left free resolution, and you can compute Tors via this resolution, and you can obtain arbitrary Tors going to the left. Tor 0 is just the tensor product, and Tor 1 left derived function, Tor 2, and so on, higher left derived functors. But here is some opposite situation where computing Tor via right flat resolution, and then it immediately implies that the left derived functors are 0. Okay, so L not is necessarily flat as well. Okay, and that's fine. So this cone psi consists of all flat modules, and hence the tensor product cone psi tensor M over A is also exact. Okay, but then again, if we go back to this standard exact sequence, it means that the cohomology of this Czech complex tensored with M is the same as cohomology of L nu complex tensored with M. Okay. The cohomology of L nu tensor over A with M isomorphically goes to the cohomology of the Czech complex tensored with M. Okay, so we proved B.
Что значит, что дельта равно плюс-минус пси?
That depends on the number. It's either psi or minus psi.
Ну, в каком случае нужно знать, как выбрать?
Well, I gave here the definition. Here you see there was some sign in the third line from the bottom, so you can find out yourself. So then you prove the universality. It remains to prove the freeness. Namely that the zeroth term is free. And it is here that we will need to shrink our y. So for this, we'll need shrink y. And otherwise, L0 mu is only locally free. Okay. So this is the statement of the last technical lemma. So a flat finitely generated a module is locally free. And you see, for example, if you take just the fraction field of our ring A, then it's certainly flat. And certainly not finitely generated and not free, not locally free. Okay, so the finitely generated assumption is essential here. I mean, just take any localization at all, not necessarily the fraction field. Just remove any divisor, localize with respect to any one element. The result will be certainly flat, but certainly not free, and not finitely generated. But for finitely generated modules, this mysterious property of flatness is just local freeness. Okay, so let's go to the next page and prove it.
Could you just explain the previous step when we proved the part B, the universality? Why do we obtain the quasi-isomorphism here? So I understand that this cone tensor M is exact, and what?
Yes. But this cone tensor M is the cone of I mean, in this business, we could just tensor everything with M.
And you say that it stays exact. This so taking a cone.
Well, I mean, not necessarily, but since we know that all the terms of our complexes in question are flat, then certainly after tensoring by M, it remains exact. So we made some work to prove that our complexes consist of flat modules. But since we know this, we can easily tensor with anything we want.
Okay.
And exactness is preserved.
Once again, to understand, so I have my check complex with shifted degrees, maps to cone, maps to L nu. Yes. Yes, by the definition. And then you say that tensor by M, I obtain again an exact sequence.
Right.
Of complexes.
Because we know that all the terms of our all the three our complexes are flat. And so when we tensor with any module M, the exactness is preserved.
And we can
just
check
because everything is flat.
Yeah. So to prove this for the exactness of complexes, you check it for each sequence of modules. I see. Thank you.
And there was some other question? No other question?
Да, что такое locally free module?
It means that when we localize it, we obtain some quasi-coherent sheaf on Y, that was the spectrum of A, and it is locally free, meaning that each point has a neighborhood. Well, when you restrict to this neighborhood, you obtain a free module. Well, it's also called projective. Yeah, if you are more familiar with this language, then I
Проективный модуль.
Yes, a flat finitely generated module is necessarily projective. You prefer this terminology? Okay. Okay, so let's prove this last lemma. So choose a point in y, and then we will produce a neighborhood where it is free, and choose well, say our module. Let's call it L, yeah, because we're just in L mu 0. So now take elements L1 and so on, Ln, giving a basis in the fiber. Say we localize and then take the fiber at y. So in other words, this is L modulo the maximal ideal of y. Okay. Then we know that this localization is a coherent sheaf. And those sections L1 and so Ln generate L tilde in a neighborhood U containing Y. Okay, we proved this a few months ago, that in order to check if a morphism of coherent sheaves is surjective, well, locally surjective, so at the level of stocks is surjective, it suffices to check it at the level of fiber. Okay, sort of Nakayama lemma. Okay, so we have a surjection from O U to the power n to L tilde, and let's say G is the kernel of this surjection. I. So we have an exact sequence 0 to G to OU to the power n to L tilde to 0. And we know that this is flat. So we have a long exact sequence. We have the fiber L y goes to 0, which is tensor with a modulo the maximal ideal y. So we get direct, well, O to the power n y, again the fiber. Then we have the fiber here, G, Y, and here we have the first store of L and OY.
Почему после тензорного умножения у нас получился слой?
Well, by their definition, the fiber is this tensor product. It's just the definition
мы
of
написали,
fiber.
что слой — это фактор L по максимальному идеалу в точке.
Yeah.
А почему это можно представить как тензорное произведение на OY?
Just by definition, I don't know. When I say this is the same as L tensor A modulo the maximal ideal.
Спасибо.
Okay, but the store is 0 because L tilde is flat. Okay, so we have an exact sequence from 0 to the fiber GY to this to the fiber LY to 0, but we know that this what was it phi. So this phi is an isomorphism. by construction. This phi, maybe I should say the fiber at y. And hence gy is 0, and hence g is 0 in a neighborhood of y. Oh, sorry, of y. Okay, hence phi is an isomorphism in this neighborhood, and hence L is locally free. I mean, it's free in this neighborhood, so locally free. Fine. We managed to prove this famous Grothendieck theorem. Congratulations. And now let's start deriving some corollaries from it. So applications. To the cohomology of fibers of morphism. So we said x, y is the fiber over a point in the base, and fy is f restricted to this closed subvariety in the total space. And let's now prove the following proposition. Well, again, we assume that f is projective. F is flat over y. And then first, the Euler characteristic chi of fy is locally constant. I mean, it's constant on every connected component of y. And also for any particular number of cohomology, for any particular degree, dimension of this degree is an upper semi-continuous function on y. So it can jump. Yeah, it is, well, how to say it? On some open subset, it's constant, but then as you approach the boundary, it can jump, and then as you approach the higher boundary, it can jump more, and so on. Okay, so the proof is a sort of immediate corollary of Grothendieck theorem. We only have to notice that when you restrict to the fiber, it means that you just take f tensor the pullback of the skyscraper sheaf, the structure sheaf of this point, y. Okay, so that's a particular case of what we studied before, right? We had before the higher direct images of f tensor pullback of certain sheaf, the pullback from y to x, and now we take m equals of y, the skyscraper sheaf at point y. Okay, so the statement is local again. We may replace y by some open subset U, where there exists Grothendieck complex K, okay, of free finite rank OU modules. Okay, and well, how it maybe I should just write it. Okay, 0 to K0 to K1, and so on, and it is finite length also. Okay, and we will know that when we restrict this complex to our point y, and then take its cohomology, then it is equal to the cohomology of the fiber with coefficients in the restricted sheaf. Okay, there's a particular case of Grothendieck theorem. So where we will apply it in this form. Okay, now let's compute the Euler characteristic of Fy. By definition, this is the alternate sum of dimension of cohomology. And this is the same. This is computed via Grothendieck complex. Why? Okay, and then again, this is the alternate sum of dimensions of those terms of complexes, well, restricted to y, and this is just the alternate sum of the ranks of ki. And so certainly this is independent of y.
Последнее равенство, почему так получилось?
The very last equality, we know that those k's are locally free, just vector bundles. So well, the dimension of fiber at any point is just the rank of this vector bundle. Yeah.
Спасибо.
Welcome. Okay, so we proved A. Now let's go prove B. And well, maybe let's start here to see what we're doing. So I have the following Z sequence. 0 goes to the image of alpha I minus 1 at point Y. Goes to the kernel of alpha I at point Y. Goes to the ith cohomology of this complex K at point Y. Okay, and also we know that the ith cohomology of our complex K at point Y is the ith cohomology of the fiber with coefficients in our sheaf. Okay, and it implies that the dimension of ith cohomology, with coefficients in Y, is the dimension of the fiber of K at Y minus the rank of alpha I at point Y minus the rank of alpha I minus 1 at point Y.
Да, когда мы вот предыдущий пункт доказывали, мы вот использовали, что размерность вот этих когомологий x, y, f, y, они равны вот размерности k, y, и t. А сейчас мы пишем, что не равны. Почему так получилось?
What do you say? I'm confused. I don't understand what you say. Say it again, mate.
Вот если посмотреть предыдущий пункт, где мы вычисляли Эйлерову характеристику f от y, мы писали вот определение, а потом следующее равенство написали.
I mean, for Euler characteristic, yeah, here.
Да, вот это равенство. Размерность когомологии x, y, f, y равна размерности когомологий комплекса k, y.
Oh, yes. Yes, and so
В
what?
пункте B мы уже так не пишем. Уже так не получается.
We are again using this. Understand? We're again using that the cohomology of xy with coefficients in fy can be computed via this complex K. We're again using
не в точности равен, получается, а там мы вычитаем уже ранги вот этих отображений альфа.
Well, when you compute cohomology, you have to take the quotient of cocycles modulo coboundaries. Yeah, I know this better than me. Yeah, and that's what I do here. Okay, so we know that this rank is locally constant. But we know that those ranks are lower semi-continuous. Right, so the rank can only drop when you specialize. Drops under specialization. Okay, so that's it. When you subtract something lower semi-continuous, you obtain something upper semi-continuous. So this is proved.
Drops under specialization. What does it mean? I thought that the rank can only jump when we restrict on.
No, the rank can drop. Like consider the vector space of matrices, Lie algebra GLM. Yeah. Then generically the rank is M, but if you go say to 0.0, the rank drops to 0. So out of specialization, the rank can drop.
Maybe I'm messing it up with
the kernel can jump, but the image can only drop.
But
the kernel jumps, the image drops.
Okay, but we have a notion of a rank of a coherent sheaf at a point, and this.
Oh no, it's something different. Yeah, but here we are speaking of rank of a morphism. Yeah, that's true. But here's the rank of morphism of locally free sheaf.
Okay.
Yeah, we'll have more of it right now. For example, like consider two locally free sheaves, and the structure sheaf of the affine line, and another structure sheaf of affine line, another copy, the multiplication by the coordinate, right? Then the rank of this morphism, well, like say psi or alpha, say alpha is multiplication by the coordinate t. Rank of alpha at any point x not equal to 0 is 1, and the rank of alpha at x equals 0 is 0. Okay. We have two invertible sheaves. There is a morphism which is actually an embedding, but embedding of locally free sheaves. But still, the rank at the special point 0 drops. Here there's another sequence 0, O, A1, goes to O, A1, and then you have the structure sheaf A0. Okay, so that's what we're speaking about. Okay, and now we want to compare the higher direct image of our sheaf F, the fiber of this higher direct image at Y with cohomology of the fiber with coefficients in Fy. And well, there is a natural morphism like this. Psi Y, but it's not necessarily an isomorphism. So in general, psi Y is not necessarily an isomorphism. But sometimes, but under favorable circumstances,
Можно какой-то пример, когда это не изоморфизм?
yes, just a moment. It is. And we'll study some sufficient conditions for it to be an isomorphism. And an example when it is not, an example when it is not. Well, for example, let's take counter example. Say Y is an affine plane, and X is its blow up at 0, and what do I want? Say let's take. Well, it contains a special an exceptional divisor. Exceptional divisor. So it's isomorphic to P1, the fiber over 0. Yeah. And this is just the preimage of 0. Away from 0, it's an isomorphism, but at 0, it is well, blowing up. So you have this P1 as the fiber. And now let's consider the sheaf F. This is the invertible sheaf OX of E. then it is known that that f 0, the restriction to the exceptional divisor itself, is isomorphic to OP1 of -1. Okay, this is well known, and well, you can immediately see it, and it is very, very well known from the definition. And then it implies that the cohomology of x0 with coefficients in f0 is absolutely nothing, vanishes, right? Because O of -1 is acyclic. It has no zeroth cohomology, neither the first cohomology, nothing at all. But the direct image of the sheaf is coherent. When we know this very well, so cannot have zero fiber at 0. Okay, I mean it's our f is an isomorphism away from the origin. So we know that this direct image sheaf is just a structure sheaf away from the origin, and its fiber at the origin cannot, it can only jump, as we just discussed with Altan. It cannot drop. It cannot be zero fiber. Okay. But you see, in this situation, there was no flatness. This morphism is not flat, and the sheaf is not flat. So this was the origin of this counterexample.
Понял, спасибо.
Okay, so well, maybe we need some terminology. So we say that the formation of direct image of f commutes with base extension and this terminology base extension is for like scalar extension. So we say this if well, y well, okay, sorry, if for any quasi-coherent sheaf on y, the nature of morphism and also for any I, nature morphism psi I of m from the higher direct image of f tensored with m to higher direct image of f tensor the pullback of m is an isomorphism. Okay, and now the next proposition that we will not have time to prove today, but prove next time, is that if the dimension of ith cohomology of the fibers with coefficients in our sheaf f is constant along y, then the ith direct image of our sheaf F is locally free of constant, I don't know, C, of rank C, and commutes with base extension in Y. Okay, so that's a proposition due to German motivation Grauert. Well, maybe in analytic situation, but then Grothendieck proved its algebraic version. Okay. So now I have to stop, but we will next time we'll prove this proposition and maybe a little bit more, and then finally our theoretical part will be over, and we will move to the very concrete applications. Okay, so that's it for today. And any questions?
Okay, I have a question about the right direct images because now I have no intuition for them. How do I understand them? Like, okay, first the most stupid question: if F is the identity map, just the identity, so what are the higher direct images of?
Just zero direct image, and it's the identity functor. So nothing happens at all, and that's absolutely clear.
Okay, yeah.
In fact, those higher direct images only go to the well, how to say, to the maximal dimension of fibers.
Can you elaborate what I mean?
Pardon me?
What do you mean by this? That higher direct images go to fibers?
Well, if all the fibers are at most curves, not more than one dimensional, then you will not have the second higher direct image. I mean, the second, third, and so on, higher direct images vanish in this situation. And for a finite morphism, for example, there are no higher direct images. And that's clear because finite morphism is an affine morphism, so there are no higher direct images. There is only that direct image itself and no higher derived functors.
Okay, and how to prove that in the case of all the dimension of fibers being bounded, we have a bound on the right direct?
Well, it requires some work. For example, we never proved that if you have an n-dimensional variety, then the cohomology of coherent sheaves only live in degrees up to n. I claimed this, and we proved this for projective space, but we never proved this in general, right?
We use check resolution.
Yes, for project space, right? You can cover Pn by n+1 opens, and that's then using Czech resolution, you can derive this. But for arbitrary n-dimensional variety, you can certainly you cannot open it. You cannot cover it by dimension +1 opens. Well, no, not necessarily. For curves, you can, but for surfaces, already not necessarily.
I see. And how to deal with this problem?
I mean, how the Grothendieck theorem is proved, you ask? Well, you can look it up in Hartshorn, for example, or in many other places. Well, or we can discuss it separately or whatever. But well, it's a non-trivial theorem.
Okay, I see. Thank you.
But certainly it has some standard topological origins, so it did not come out of blue. It was known, say, exactly to Czech in the standard topological, in the standard point set topology. It was already known. Then Grothendieck generalized it to algebraic geometry.
Можно тоже спросить?
Yes, certainly.
Вот пусть у нас есть семейство
Yes.
И каждый его слой гладкий. Тогда, значит, и морфизм сам, пускай плоский, да, если семейство.
Well, it's even smooth, I would say. Yeah, if all the fibers are smooth. Well, I mean, scheme theoretically, yeah. Then the morphism is
Плоский
smooth as
морфизм
well.
с гладкими слоями. Вот, тогда я слышал
Yes.
утверждение, что все слои друг другу гомеоморфны. Геометрические слои этого морфизма гомеоморфны. Это правда?
You mean if we are over complex numbers, yeah, and then consider the classical
Yes.
topology, yeah? Well, then as a theorem of Ehresmann, you can introduce some flat connection, yeah. And then integrate this connection. Yeah, that's true. Yes.
А в алгебраической ситуации это не так?
Oh no, certainly you can have a family of elliptic curves. Yeah, they are not isomorphic at all. Absolutely, or just heterogeneous curves, or not necessarily curves. So absolutely, it's a rather rough statement about differential topology.
Хорошо.
So these well, smooth manifolds are all diffeomorphic, but already in complex analysis it's wrong. They are not biholomorphic. They are only diffeomorphic in real topology.
Так, ладно, а вот про relative dualizing sheaf вопрос.
Yes.
То есть вот, он играет вот похожую, да, роль, как обычный dualizing sheaf в двойственности Серра.
Yes, certainly, yeah.
То есть есть аналог двойственности Серра, где вот там мы тензорим на relative dualizing sheaf.
Okay, yes.
Это, ну, я просто плохо понимаю, что...
Then you will use not the absolute cohomology, but the direct image to the base. Yeah. So it'll be some statement about direct image to the base. And in fact, I formulated it last time, or maybe a week ago, I forgot. At some point, I formulated this relative version of Serre duality. In answering Altan's question, I formulated it maybe a week ago.
Так. Ладно. И я вот вечно путаюсь как бы с понятиями слой пучка над точкой и, значит, вот геометрический слой пучка. Что это такое?
Well, just in Russian, there are not as many words as in English. So in English, you have stock and fiber. In Russian, you can only say слой.
Yeah, fiber.
Or maybe for stock, you can say
ростки.
Росток. Yeah, right. Right.
Я вечно путаю, вот есть, скажем, векторное расслоение, это локально свободный пучок,
right.
Скажем, конечного ранга. Вот у него есть слой над точкой. Значит, это векторное пространство размерности, который есть ранг этого пучка. Значит, а есть...
Or you can take росток. Stock.
Вот можно взять это векторное расслоение, взять пучок его сечений.
Yeah.
Вот, и взять у этого пучка...
The corresponding locally free sheaf, yes, and that will be the localization of your structure sheaf to the power, well, a direct sum of few copies over rank many copies of your structure sheaf.
Это вы говорите сток пучка
сечений.
сечений.
The base field, the fiber will be a finite dimensional module over the base field, and the stock will be the free module over the local ring of this point, or the same rank.
Вот про вот fiber, как он выглядит?
It is the finite dimensional vector space over the base field.
и над любой точкой, получается, такой есть поточечный изоморфизм.
Isomorphism of what? I don't understand.
Файбер и
So
конечномерного
fiber-
векторного пространства над К.
Oh, yes, certainly, yes.
Поточечный такой неканонический изоморфизм над каждой точкой.
If you wish, yeah. Certainly, there is no preferred base. So in order to construct some preferred canonical isomorphism, you need some particular base. There is no particular base.
Хорошо. Спасибо. А вот base extension это то же самое, что base change?
Well, you usually say base change when something maps to y and you take a pullback. Yes, like when z maps to y and you take, say, Cartesian product of x and z over y. And here it's not quite this. Yeah, you have some module over oy and you tensor with this module. So it's more like extension of scalars. And that's why I call it extension of base instead of base change. But certainly it's similar because this module M can be a direct image from Z. So it does have something in common.
То есть нет такого, что одно есть частный случай другого понятия.
No, I don't think so.
Два разных.
Well, in case your base change is affine, then it reduces to this indeed. The affine base change does reduce to the base extension.
Why? How it reduces?
Да, why?
Just take the direct image under this affine morphism. We know that affine morphisms are the same as just algebras over the structure sheaf OY. So take this M to be the direct image algebra, quasi-coherent.
So M is a direct image of structure sheaf of
Z.
Yeah, I see.
If Z is affine.
Okay, so both spaces are affine, and the morphism is affine too. Is it the case?
No, I only need that the morphism from Z to Y is affine. Then it's the same as a quasi-coherent OY modules algebra. OY algebra.
Okay, that's one of the equivalent definitions of affine morphism.
Yeah, for example.
Okay.
Okay.
Спасибо.
So if yes, there are no more questions, then I am saving the note and stopping the recording.